All right, problem 7. Small rigid object carries positive and negative 2.05 nanocoulomb charges. It is oriented so the positive charge has coordinates negative 1.2 millimeters and 1.2 millimeters, and the negative charge is at 1.35 millimeters and negative 1.3 millimeters. Okay? That sounds like a dipole. Find the electric dipole moment of the object. Okay, so electric dipoles are, for the most part, a handful of equations that you have to know. If you're given a cheat sheet, you can just be able to recognize them and then apply. We have dot products and cross products, and that's pretty much all we got here. I don't memorize them because I don't. So I'm going to Wikipedia them. Electric dipole. All right, let's see what we got here. So we're supposed to find the electric dipole moment. Bam, right here. P equals QD. All right. So we're going to start by drawing a picture, just like pretty much every other time in life. So I'm going to draw my, here's a plane, and we have at negative 1.2, this will be negative 1, this will be negative 0.2, this will be 1, this will be 0.2, right up here. Negative 1.2, 1.2, and then we have 1.35, negative 1.35, so right about here, okay? 1.35, negative 1.3, there we go. So we have these two charges, and then there's a terrible line. Wait a sec, I got a line tool. Why don't I just use the line tool? Nope, that's text. Nope, that's shape. There we go. Ooh. What if I get that direction wrong? I'll just do a line. That way I can draw the arrow later. There we go. Nice. Well done. Well done. Ooh, I can make this into a triangle. There we go. This is going to be great. So exciting. All right, you come over here. Adequate. You come down there. And also has a sad triangle. As opposed to a cute triangle. No, we're dropping it there. Okay. So we need magnetic dipole, which this is also the symbol for momentum, but it's not momentum. Different concepts, do not confuse the two, even though they have the exact same symbol. All right, so the question then, since these are both vectors, is what is the direction? So the way I remember this, and I just use stupid mnemonics for everything in life. So we have a positive charge and a negative charge. So the positive charge is going to have arrows, forces going out in all directions, as such. And then the negative is going to have arrows coming in all directions, as such. So turns out there are two completely different conventions for electric dipoles. Electric dipoles used commonly in physics and chemistry. So I'm going to redraw just the center part here because that's all we care about for this, really. So we have a negative and a positive. So I like to think of physics as done outside. You throw a football, that's physics. Trajectory, blue, blink. It's done outside. So the convention for physics are the outside vectors. So the magnetic dipole in physics goes from negative to positive. Now in chemistry is done indoors, like in a laboratory and that sort of thing. I know chemistry can be, it's an analogy, you're supposed to, or a mnemonic. You're supposed to keep this in your mind and remember it forever. It's not supposed to make sense. Chemistry is done indoors, like, in labs with beakers and such. So it's the inside vector that matters for chemistry. So chemistry goes from positive to negative. Physics, done outdoors with footballs and baseballs and manly sports, because physicists are better than chemists. Bam, take that. I don't actually mean it. I just said that to cause controversy. So goes from negative to positive. So physics dipoles go this way. Okay. So now I just need to figure out which one of these is negative, which is positive. All right, this guy right down here is negative. So this guy is negative, and then this guy is positive. I gotta find out what the charges are. 2.05 nanocoulombs. 2.05 times 10 to the negative 9th coulombs. All right, so we got that part. So we need to multiply it together, and we need it in terms of, was it I and J? I and J. All right, so we need to break this down. So let's see here. These are the x components here. And if we do 1.35 plus 1.2, we get 2.55? I'm going to say 2.55. So this right here will be 2.55, and it goes from right to left, so it's going to be negative. And then it's going to go down from 1.2 to 1.3, which will be 2.5. Okay, that seems reasonable. And it'll also be negative. Because it goes, nope, these are positive. Because it goes from negative to positive, negative to positive. So the y component will be positive, but the x component will be negative, because the vector travels in the negative x direction, but the positive y direction. So then we're going to do 2.05, which is the charge, times 10 to the 9th, times, and I'm going to do x first, 2.55, and that'll be the I direction. And then we'll do 2.5, and I'm going to do the charge first again, just to stay consistent. Oh, and then it's millimeters, so 10 to the negative 3rd. So 2.05 times 10 to the 9th times 2.5 times 10 to the negative 3rd. And these will be J. And this guy will be negative. All right, that seems reasonable. All right, but now I'm going to have to Wolfram this, because I do not want to do that in my head. Not saying I could, just even if I could, I wouldn't want to. So 2.05 times 2.55. I don't know, it's like what, 5.2? 5.1. 2.05, isn't it? Why did I put a 2.05, 2.55? Yep. And we get 5.23. 5.23. Scroll over right here, we got 5.23. Negative. And it's times 10, because we got negative 3 here, negative 9th here, times 10 to the negative 12th. I. Okay, got that one. Bam. I don't know what the units are, so I'm just going to look and see whatever it says in the problem. Now we need the J component, which is 2.05 times 2.5. Just take off one of the extra 5s. 5.125. 5.125 times 10 to the negative 12th. And we have J. Got it. All right. So now, right up here, we'll write those guys in. So 5.23 negative 5.23 times 10 to the negative 12th, and 5.125 times 10 to the negative 12th. All right, so that is the electric dipole. Not to confuse with the magnetic dipole, which we will get to probably in future problems. All right, so now we have the object is placed in an electric field of 7.8 times 10 to the 3rd minus 4.9 times 10 to the 3rd, i's and j's respectively. All right, so I'm going to draw this out. So 7.8 is kind of like twice 4.9. So let's see here. 7.8, I'll say this is 7.8 right there. Right there. That's 7.8, and then we have, I don't need 7.8, about right here, and then 4.9, negative 4.9, I'm going to say is right about here. So we have an electric field that goes from here, and an electric field goes from here through the origin off to infinity. Okay? And we know the electric field goes from the origin to 7.8 and negative 4.9. So electric field goes from the origin to this point right here. I basically did like 2 to 1. So the important part with that is I'm going to change pens to red to get a little bit more contrast on this. Is that then tells us how it's going to affect the dipole. So electric field goes this way and here. So these are going to be the infinite plate charges that I use whenever someone mentions electric field. So if it goes that way, it goes from positive, which I'm going to say are up here, this way, to the negatives, which are over here. All right? So we know this is a negative charge here. This is a positive charge up here. So the positive charge is basically pointing at the positive charges, and the negative charges are pointing at the negative charges over here. So basically, if you think of a dipole as kind of a spring that's going to try to align itself with the electric field, this spring is about as spring as it can get before it springs back. If the dipole is exactly lined up opposite, basically the positive is pointing to the positive, the negative is pointing at the positive, as soon as you let go, it's going to spring back and align itself with the electric field. So this is a very small angle between the two, and so that's going to give it a lot of energy, or at least a very high percentage of its maximum potential energy. Think of it as a spring, where this is a compression spring right here. Like this. And the closer those two lines get to each other, the more energy you're going to get from that spring. And then, of course, you're going to have one down here as well. All right. So now we've got the concept down. The object is placed in the electric field like that. Find the torque acting on the object. All right. So this is just going to be another formula. So the idea is it's going to have maximum torque when the two are perpendicular to each other. Right. So I'm going to write out the formula for torque real quick. By write out, I mean look up on Wikipedia. Torque equals electric dipole cross the electric field. Okay? Torque equals magnetic dipole cross electric field. Now, normally I just do right-hand rules and kind of wing it, but they actually want numbers. So we're going to have to find some numbers. All right. So I'm going to start by, since we need to find a cross product, we're going to write it out as finding the determinant of a 3 by 3. And we first need to know what our two vectors are. So we're going to have negative 5.23. At this point, I'm going to leave off the exponents times 10 to the whatever, just for simplicity's sake. If you're doing this for a test, I would recommend writing them in, just because you don't want to get dinged for stupid points that, you could do like times 10 to the negative 12, times 10 to the negative 12. That way it doesn't interfere, but that way the grader can see, oh yeah, you actually understand what's going on. And if nothing else, you can ask for a regrade later and show that, yes, you had it written in there and you understood the concept. But trying to fit that into these little boxes would just be a pain. All right. As you can kind of see it as a pain right there. 7.8, negative 4.9. All right. So the way we're going to do this, I think I can make a better determinant than that. All right. I, J, and K. Hat, hat, hat. So if you don't know how to take the cross product of vectors using the determinant, find a YouTube video. Do determinant, vectors, Yeah, cross product. Cross product of two vectors. Now that'll give you an idea where to go. So for the first vector we have negative 5.23, 5.125. And the reason I put this one on top because it's electric dipole, which is this guy, cross the electric field, which is second. And these are, of course, all vectors. And then there's no component in the k direction. So then we have 7.8 and 4.9 negative. Okay? So then we're going to find it in each direction, the I direction, the j direction, and the k direction. So the way you do this is you cover up this portion. I grab myself a box. Is that? Can I fill that in? Fill in. No, it's not what I wanted. No. Haha. Shazam. So the way you do it is, go away, useful box. No, go away. You take it, you cover up, to find I, you cover up this section, and you do a 2 by 2 determinant. So you do 5.125 times 0 minus 0 minus 4.90. You then go to j, but this time you do it negative j, and you do negative 5.23 times 0 minus 0 times 7.8. And then you'd have the sign switched on the j, so it'd be times negative j direction. Well, since those both have zeros in it, they're going to be 0. Then we're left then with our k. Should have made a box a little smaller. There we go. So for k then, which is the only one I'm going to write down because it's the only one that's not 0. And intuitively, this kind of makes sense as what you want, because when you cross two vectors, you get a 90-degree. You get a third vector that's perpendicular to both of them. Well, if both the electric dipole and the electric field are in the xy plane, or the ij plane, then the resulting cross product is going to be in the k plane. So we're going to do negative 5.23 times negative 4.9. And it's going to, since they're double negatives, going to plus them up. And I'm going to subtract 5.125 times 7.80. Okay? So I'm going to wolfram this real quick. And we have 5.23 times 4.9. And we get, 25.63. And then we're going to have, I think I'll use another wolfram window, 5.125 times 7.8. Yep. And that gives us 39.98. Minus 39.98. All right? Subtract one from the other. Negative 14.35. Negative 14.35. All right. So let's make sure, and it's supposed to be a negative there, negative. Make sure that makes sense. So 5 times 4 is like 25, yeah. 5 times 7 is like 35, a little bit more, okay. This is the big number, it's bigger by about 14. Got it, yep. I totally believe that. Okay, so these worked in opposite directions, and they lost a lot of the energy that they could have potentially had, because cross products are biggest when they're perpendicular. So for a cross product, for the magnitude of a cross product, A dot B, by dot I mean cross, gosh, so A cross B, the magnitude is equal to A times B, magnitudes, times sine of theta. And the way I remember its sign is because it'd be really convenient if it was a cross product, because, or a cosine, because cross product cosine, both start with C, be really nice, but that's a trap. Don't fall into that trap right there, because that's a false friend right there. The cross product is not cosine, therefore it has to be sine. And sine is going to be biggest when they're 90 degrees apart from each other. And looking at the picture we drew, they are not, specifically not 90 degrees apart from each other. They're specifically close. So, oh, need to add a direction here. So, and this is K. So the way we're going to do this then is find the torque acting on the object. All right, so the torque is going to be in the K direction. I'm going to say this is, the torque is 14.35, and it's going to operate in the negative K direction. I could have, maybe it'd be fine if you said negative 14.3 and positive K. Oh, you need a negative in there somewhere, and it's however the problem wants you to enter it. So for the torque is a cross product. And it's as similar as it was in, I guess, physics 1, where torque equals R cross F. Except this time we have P cross E. So, same idea. Get rid of that guy, because he bothers me. Find the potential energy of the object field system when the object is in this orientation. Okay, we can do that. So, let's go over here, electric field, or to Wikipedia. And let's find potential, no. Potential energy. Pretty sure it's a dot product. Maybe if I just do a Control F, potential energy. It's not what I wanted. Not what I wanted. Well, I'm just going to give you this one and say it is. So, nah, I could probably look this up. When Wikipedia fails me, Google never will. Potential energy of a dipole. Haha. Must have looked this guy up before. All right. Let's do hyperphysics. Hyperphysics is fairly reliable. D over 2 sine of theta. And I'm looking for a dot product. Torque equals EQD. EQD is the, nope, that's the torque. I don't want the torque. Energy. Aha, there we go. EP, negative P dot E. Okay. So for the energy, so I'm going to say they like to use U, which I'll go for that, equals negative magnetic and electric dipole dot electric field. So we're going to use dot product. So for this one then, we're going to do, scroll up, there's our two vectors written right here. Oh, wait a sec. I forgot to put units on the torque. I almost led you guys astray. All right, so this guy, see, maybe you should write the exponents in every time. All right, so we have 10 to the negative 12 times 10 to the third, so 10 to the negative 12 times 10 to the third will give you 10 to the negative 9th. 10 to the negative 9th. So add that guy in right there. All right, back to more pressing matters. So these guys, 10 to the negative 12th. This will be 10 to the third. All right. So for P, we'll do, so to do, if you have, I'll do it this way, x1, y1, and x2, y2, and you want to dot product these guys, the way you do it is x1 times x2 plus y1 times y2. When you do a dot product, it results in a scalar, not a vector. So we'll do 5.23 times 7.8. And then 1 is 10 to the 12, negative 12, 1 times 10 to the 3, so we'll get negative 9. Plus 5.125 times 4.9. And there's probably some negatives in here. These guys are both negative. There we go. So 5.23 times 7.8. 5.23 times 7.8 plus 5.125 times, was it 4.9? 4.9. I know these are all supposed to be negative. I'm just going to make it all negative in the end. So 5.23, 7.8, 4.9, 65.9. 65.9. And that would be times 10 to the negative 9th. And joules. Got it. All right. So this guy, 65.9. 65.9 times 10 to the negative 9th. All right, next question is, assuming the orientation of the object can change, find the difference between the maximum and minimum potential energies of the system. Okay, so the maximum, think of this back in the idea of the spring here, the maximum potential energy is going to be when this spring is fully compressed, i.e. the positive charge here exactly lines up with the positive charges from the electric field, and the negative lines up exactly with the negative. And then the minimum energy would be when the positive exactly matches up with the negative, and the negative exactly matches up with the positive. So our dipole is like this, where this is the positive side, and then this has maximum energy, and then when it rotates all the way exactly almost from maximum to minimum will be 180 degrees. So when it rotates 180 degrees, then it will go from maximum to minimum. So minimum is going to be 0. So all we really have to do is find the maximum minus 0. So find the maximum. And the angle then, right here, this angle, theta, will equal 0 for maximum energy. So we have a dot product down here. We can find the magnitude of a dot product. Ooh, that should be negative. This negative then goes into both those negatives and becomes positive. Yes, that makes sense. All right, will be, so the other way to do a dot product, at least to find the magnitude, to find a dot product would be time electric dipole times electric field times, is it cosine? It's cosine. Because cosine should be for the cross product, but it's not, it's a trap. So cosine is for the dot product. Yes. And the maximum that cosine of theta can be is 1 when theta equals 0. Therefore, this equals 1. So this is going to be the magnitude of P times the magnitude, oh, that was odd, P times the magnitude of E. So we need to find the magnitudes of these guys. Blah. Okay, let's do this. So the magnitude of the first one is 5.23. All right. Probably be easier for me to just rewrite the whole thing, but I'm not going to. I'm going to be stubborn. So we want to find the square root of the first one. squared plus the second one squared. And that will give us the magnitude, so 7.32. So this guy is 7.32 times 10 to the negative 12th, which makes sense because 7 is a little bit bigger than 5, and yeah, 7.8 and 4.9. All right, and that gives us 9.21. Plus 9.21, by plus I mean multiply, times 10 to the third. Multiply those guys together. Is it 7.321? No, 7.32. Gives us, like, I don't know, 70? 67.42. 67.42 times 10 to the negative 9th. All right, and that is the maximum energy, which is also the maximum minus the minimum, because the minimum in this case would be 0. 67 is also bigger than 65.9, therefore it makes sense that it'll be bigger. But it's not a lot bigger because the it's pretty well aligned opposite of the electric field. By it there, I mean the dipole. All right, let's read this one more time, make sure I'm not going crazy. Assuming the orientation of the object can be changed, the object being the dipole, find the difference between the maximum and minimum potential energies of the system. Yes. Yes, I will believe that to be the case, and I will say that that is true. All right, so this is how you do this problem. The key parts to take away from this is electric dipoles exist, and specifically in physics, they are drawn from negative to positive. If you want to find the torque, it's going to be a cross product between the electric dipole and the electric field. If you want to then find the energy, you're going to then use the dot product. It makes sense that the torque would be the greatest when the two are at 90 degrees from each other, and the energy will be the greatest when the electric charges are exactly opposite of each other. And from that, if you forget which one's dot product and which one's cross product, you can then guess and check and see which model aligns with your natural understanding. All right. That's it for this one. I don't think you'll use this too much. You might have one test question over it. So I would learn this just well enough to be able to pick out the right formulas and then go from there. Don't spend forever learning about electric dipoles, because this is pretty much all you need to know. All right? Good luck, and I will see you on problem 8.